In our last two classes, we spoke about sequence. We defined it and took some examples. Then we proceeded to talking about the two most popular kinds of sequence that we have, which is the arithmetic progression and the geometric progression. So in the last class, we spoke about the arithmetic progressions. But today, we are going to look at strictly at what we refer to as the geometric progression. The geometric progression. That's called the GP. So do have it in mind that we said that another name for progression is termed sequence. So the question is, what is geometric progression? So in simple term, or a simplified term, a geometric progression can be defined as a sequence that is characterized by common ratio. You know, for AP, we did say it's a sequence that is characterized by common difference. So this time, we are replacing common difference with common ratio, actually. So another name for GP, or geometric progression, is called exponential sequence, actually. So that is the definition. The definition is that what? A geometric progression is a sequence that is characterized by common ratio. And it is defined, the end step of a geometric progression is defined by u subscript n equals a raised to the power ar raised to the power of n minus 1. This is the end term of an arithmetic of a geometric progression. When you have our un is called the nth term, and when we have our a is called the first term, and when we have our r is called the common ratio, and when we have our n is the number of terms in the progression. Number of terms in the progression or the sequence, as the case may be. Then these are the definitions of what each of these terms in the geometric end stands for. Then imagine that you have our u1, u2, u3, u4, all the way down to say un minus 1, un plus 1 to be the terms of a geometric progression. Then our common ratio is defined as simply defined as here. It's defined as r equals u2 over u1 equals u3 over u2 equals u4 over u5 equals all the way down to un all over un minus 1 equals un plus 1 over un. All I'm trying to explain to you is that the common ratio is the succeeding time over the preceding term, succeeding time over the preceding term, the immediate preceding term, the succeeding term over the immediate preceding term. When we have the answers to be same, then we call this the common ratio, and it is only the common ratio that qualifies a sequence to be called exponential sequence or geometric progression, as the case may be. So I'm going to be going to explain the terms of a geometric sequence. Okay, like I said, we're going to be talking about the terms of a geometric progression. So terms of a geometric progression. So what does it look like? Now, the first term of a geometric progression is a, while the second term is ar, while the third term is ar squared, while the fourth term is ar raised to power 3, while the fifth term is ar raised to power 4, and it goes on and on to un equals ar raised to power n minus 1. These are the terms of a geometric progression. The first, the second, the third, the fourth, the fifth, and the nth term. How do I derive it? When my n, when n equals to 1 here, I have u1 equals to a 1 minus 1. If you remember from the last 2 videos I made about sequence, whenever you see n, you are replacing n alone with 1. So what does it become? This one automatically becomes u1 equals ar raised to 0. And anything raised to 0 for units is 1. So a times 1 is 1. So u1 is a. That is how we got our u1 to be a. Then when our n is 2, then our u2 equals ar 2 minus 1. It becomes ar raised to the power of 1, and that is ar. That's how we got this. Then when n is what? When n is 3, what do we have? We have u3 equals to ar 3 minus 1, which eventually give ar equals to 2. That's how we got this. And that's how we keep getting them all the way downwards. So that is why we call it a geometry progression. So that these are the curves that can be found in a geometric progression. So let me just take, let me just quickly run us through how we can solve for the common ratio of the geometric progression, giving some specific terms. Solving for the common ratio of a geometric progression. So, to solve for the common ratio of a what? Of a geometric progression, GP. So for instance, we have 1, say you have 2, 4, 8, 16, 32 all the way down. We got 2, say you have 81, 27, 9, 3 all the way down. Then we got 3, say you have 1 over 8, 1 over 4, 1 over 2, 1, and it goes on. And we have got 5. So you have 0 0.1, 0 0.01, 0 0.001, 0 0.0001, and so on. So let's consider these examples for instance. I'm asked also for my common ratio. Do you understand? I will do some when I need to do the other ones. The only thing you need to do is to understand the concept and the process for solving. That's the only convenience. So let's see solution. Number 1. Solution. I have number 1 to be what? To be 2, 4, 8, 16, 32, all the way down. So I label this one U1, I label this one U2, I label this one U3, I label this one U4, U5. And I will then remember that my common ratio R is simply given as my U2 over what? U1, followed by my U3 over what? U2, followed by U4 over what? U3, followed by U5 over what? U4. So if that is said, what will I have? My R, my U2 is what? 4 over 2, because my U1 is 2, and it must be equals to 8 over 4. My U3 is 8, and my U2 is 4, and it will be equals to 16 over 8, or equals to 2 over 16, and 2 here 1, 2 here 2, 4 here 1, 4 here 2, 8 here 1, 8 here 2, 16 here 1, 16 here 2. Then I will have 2, 2, 2, 2, meaning that my common ratio is what? Is 2. Now, what qualifies this sequence, we call a geometric sequence, is because the common ratio, it has a common ratio of 2. If at a point we have 3, at any point, then it's no more qualified to be called a geometric progression, because a geometric progression must have common ratio all through its sequences. So, look at number 2. In the same light, we have 81, or maybe I should just do number 3. I think it's number 2. Then I have 1 over 8. I have 1 over 4. I have 1 over 2. I have 1 all the way down. I label this on my U1, here my U2, here my U3, here my U4. Then your formula still remains the same. U2 over U1, 1 over 4 over 1 over 8. Comma, U3 over U2, 1 over 2 over 1 over 4, U4 over U3, 1 over 1 over 2. This is what I'm going to solve. Now, that being said, let's just do this part already. It means that I'm going to be, look at what I'm going to have here. I'm going to be having my common ratio R to be equals to 1 over 4 multiplied by 8 over 1. then must be equals to 1 by 2 multiplied by 4 over 1, and must be equals to 1 multiplied by 2 over 1. So 4 here 1, 4 here 2, 2 here 1, 2 here 2. My common ratio equals to 1 times 2 is 2, 1 times 2 is 2, 1 times 2 is 2. So my common ratio is 2. Meanwhile, don't assume that because I have 2 here as my first example and 2 here, so all common ratio will be 2. That's just a coincidence. So the same way I've done this number 1 and number 3, you can also do number 2 and 4. Just follow the process. This over this must be equals to this over this must be equals to this over this, and then you get a common ratio for that answer. So let us take just one simple example that I believe is will be enough to explain all that I've said so far. So follow me.